much all those
So
things.
I got into upper level classes, and now I'm like, I can't miss no days. I'll get behind.
So they're not going to class, Dan, and I was just like, I know I'll need the material we're covering.
Okay, well, I'm gonna
Start with that.
shut the door. Oh, there he is. Okay, so today we're covering section 4.2 in the notes, and this is on the LU factorization. Last week in class and in lab, we talked about how it's not practical to compute x for multiple right-hand sides b with the same a. So what we want to do is we want to store the upper triangular form. We want to store an upper triangular form of a in such a way so that we can apply it to b multiple times to solve for different x's. So as we discussed in lab, anytime we subtract mij times rho j from rho I, which is equivalent to saying like rho I minus mij times rho j, to eliminate aij is equivalent to what? We did this in lab. So anytime you want to apply these row operations to a matrix, we can also do what that has the same effect? We can multiply by those elementary row matrices, right? So equivalent to multiplying by the elementary row matrices. So I'm going to close this. That's better. All right, so now when we were in lab, we discussed what these elementary row matrices are, and it was just taking the negative sign of the multiplier and putting it in the place of whichever element you're trying to eliminate. So now we'll just define that formally. And I'm going to call these Mij now, where I and J are the row and column of the element that we're trying to eliminate. These correspond to like the E1, E2 that are in the notes. So we have this matrix, and it's an identity matrix, except for, so say here's 1. We have this multiplier in the matrix, Mij, all the way down to 1. And then this is going to be up to 0. To 0. So it's just the identity matrix, is that we have the multiplier in the place of the element that we're trying to eliminate with this particular elementary row matrix. So Mij is in row I and column J. So before we get into anything else, what I want to do is take a look at the inverse of a matrix of this form. I guess we can come over to this board for that. inverse of Mij, well, we know that Mij inverse times Mij is equal to identity. So we can just set up, I have a 3x3 example we're going to set up, and we're going to take a look at what the inverse of this actually looks like. So, Mij is what's going to contain all of my unknowns, right? So I'm just going to call those x11, x12, and so forth. And that's what we're going to solve for. x13, x2. So those are all of my unknowns.
So that's in my J.
This is Mij inverse.
Okay.
So those are the ones that we don't know. Now this one is going to be Mij. So it's just, again, the identity matrix with the multiplier in the place of whichever one you're trying to eliminate. So this is identity. And we'll put Mij right here. Alright, so now I've set this up. So this is Mij inverse, this is Mij, and then this is identity right here. So now just carry out the multiplication and we can solve for the unknowns. So multiply this row times this column. x11 minus x13 Mij equal to 1. And let's see, I worked through the, okay, so now I'll multiply this one times this one. Yeah. So that's, the only thing we get from here is just that x12 equals 0. And then, and lastly, we get x13 is also equal to 0. So this is row 1. And then let's take a look at row 2. So that's going to be x21 minus x, let's see, this one times this one, and then x23 times Mij is equal to 0. Then you have x22 equal 1 and x23 equals 0. So that's row 2. And then lastly we'll deal with row 3. So we've got x31 equal to x31 minus x33 Mij equal to 0. x32 equals 0. And then x33 equals 1. So that's row 3 now. So now we can solve for all of our unknowns, where we actually already have most of them. So here we need to solve for x11, well we know that x13 is 0. So that means x11 is equal to 1. And we already have the other two. So we have row 1 now. Here, x23 is equal to 0, so we plug 0 in the place here. So then we would just get x21 equal to 0. And so now we have row 2. And here for row 3, we're going to plug x33 equal to 1 in here. So I have x31 minus Mij equals 0. So x31 equals Mij. So now I have, well, here and here. So I have row 3 now. So now I'm just going to plug these into my matrix. So 0, inverse of a matrix, of an elementary row matrix. And the only difference is that instead of having a negative multiplier down here, it's positive. So we just needed to take a look at, because we're going to be using the inverse of these elementary row matrices in the LU factorization. So now that we know what the inverse is, we can apply that to the LU factorization. Okay, so now,
Is the transfer supposed to be equal to the original?
do what?
Like, that's MIJ right there, and then, are they supposed to be the same?
Right, so this
Yes.
is MIJ right here. And then this,
Yes.
yeah, they're supposed to be similar. The only difference is that one is negative, and that's because of the structure that it has. That it's almost diagonal.
Oh, yeah, I see those.
Okay, yeah, so they're almost the same, but the difference is that one is positive and one's negative. Okay, so now, if we define, or if we let A1 equal A, then A to the K plus 1, is the matrix obtained by eliminating elements of column K. In AK. Okay. So what we're looking at now is that, so this is just like we were doing in lab. AK plus 1 is our new updated matrix, and it's obtained by multiplying this MK, this multiplier matrix, times the previous A. So this A has been updated to remove, to eliminate up to K elements, and now we have K plus 1. So just like we were doing in lab, when we would have A6, we would multiply by E5 or M5 times A5. And so now let's define MK. So that was MIJ that we were looking at over there, where we just have the multiplier in one place in the elementary row matrix. But here in MK, this is actually where we stack all of the multipliers for a given column K. So we got 0, 1, 0. So we have our diagonal here, and then we have M K plus 1 K right here, all the way down to negative M NK. So all MK is just we're taking these, well, I don't want to refer to that word. We're taking and stacking the multipliers for a given column. So it's just notation to refer to that. So negative mk plus 1k through negative mnk are on the column k. So we say all of that to say this. So now when we look at U, we got U from applying all these elementary row matrices to A, right? So the last updated A, which would be which one? The nth one. So we can say U is equal to AN. But then we want to take a look, well, how do we get AN? We've discussed this already. Let's say we have A1 and we set it equal to A. Then AK plus 1 is equal to MK times AK. And we can do this all the way down to AN. And AN is equal to MN minus 1A n minus 1. And that is equal to U. But we don't really know what AN minus 1 is. So we need to look at this a little bit further. So what I did was I just constructed like a 5 by 5 example, and we're not dealing with the actual matrix, but we're just going to take a look at what happens here. So if A is equal to A1, then A2 is equal to M1 A1, A3 is equal to M2 A2, A4 is equal to M3 A3, and then A5 is equal to M4 A4. And so we've convinced ourselves that this is true just by that right there. But we want to come up with a better way to represent U with things that we know. And we don't necessarily know what these intermediate steps for A are. So now what we want to look at, we know that U is equal to A5, right? Because that's the last updated matrix. Now from this right here, we know that A5, but we don't know what A5 is, right? Because we'd have to go through the process. So we know that A5 is equal to M4 times A4. So we'll replace that. But here we don't want A4, so we'll replace it with M3 A3. So we have M4 times M3 times A3. We'll do the same kind of replacement. So M4, M3, M2, A2. So y'all can see where this is going now.
Just taking the product of
the multipliers.
Times the matrix A, right?
Yes, and it's going to multiply the matrix A, and then we've already said A1 is equal to A. So M4, M3, M2, M1 times A. Okay, so all of that is equal to U now. So let's see, quick question. If all of that is equal to U, then we can do the same thing for Y, right? So Y would also be n to n minus 1, whatever our n is, all the way up to n1 times b. So whatever we apply to A, we can also apply to U. So now this is sufficient to say that U is equal to n minus 1 m to the n minus 1, m1, up to a. Okay. So now that we've examined the upper triangular part, we've looked a lot at the upper triangular part, and we know that the upper triangular part is the result of Gaussian elimination. But now we want to take a look at the lower triangular part. So, unit lower triangular matrices.
So when we saw you was gonna give us the upper triangular of that matrix A.
Yes.
And is
So
K gonna be the like size?
K is alright, so if we have, look at this. N is the size of the matrix. K in the algorithm, so when we loop over this, we have 4 I equals, let's see, 4 I equals, we're starting in the, what is it for I?
N. Oh, N minus 1.
Okay, yeah. N minus 1 up to 1, and then we have a loop for J. And those indices are I plus 1 through N. Okay. And
But
then
the I starts at N. Not N
I
minus 1.
equals
Okay.
N.
N through 1. Okay. And then J loops over I plus 1 through N. So then we have another loop for
wait.
K. What is it?
I was looking at the wrong algorithm.
Okay.
Are you
Yeah.
talking about
Gaussian elimination, yeah.
1 up to N minus 1.
That's what I thought. And then this one is
It's
I
J,
plus 1.
J plus 1 all the way to N. Wait, for I. Yeah, for I.
The first was J.
J.
J,
The next one
I.
I. Yes.
Okay. So now we're good. So what happens in Gaussian elimination is we have our column, which goes from 1 to N minus 1, our row, which goes from I plus 1 to N, and then K is what's being updated in the upper part, in the upper triangular part. So your question about K was what? Where K is?
I was just wondering what it equals, but.
Well, K is just going to be like, so if it's like, here's our upper triangular part. So, it's just all of these elements that we're updating.
It's, okay, so it's just gonna start with the K column, it's gonna go all the way over to the form matrix.
Yeah.
Okay, that makes sense.
Okay.
That works, sorry.
No, it's okay. So, well, okay. Alright, so before we were learning about upper triangular matrices, where Aij equals 0, for I greater than J, and we call this matrix U, so Aij equals 0 for I greater than J. So we call that matrix U, where U is equal to X times Y, because Y is our updated right-hand side. And that is solved by that substitution. Where U is n by n, upper triangular, non-singular matrix, if and only if the diagonal elements are not equal to 0. So So now we look at the lower triangular matrix. Where aij equals 0 if I is less than j, and we're going to call this matrix L. Because it's a lower triangular matrix. So we're going to see how to solve systems of the form Ly equals B. And so the way we solve these type of systems is called forward substitution. Okay. Alright, so forward substitution is really similar to back substitution, because we're dealing with triangular matrices. Okay. So like I was saying, we want to look at solving a system of the form Ly equals B, because we need to be able to do that to update B. So before we do that, we're going to look at some properties of triangular matrices. So some properties of triangular matrices is the product of two unit lower or upper triangular matrices is also unit lower or upper triangular. So that's just saying if I multiply a lower triangular or an upper triangular unit matrix by a lower triangular or upper triangular unit matrix, then we get the same thing out. Another property is, and I'm going to use Dr. Lambert's abbreviation from here on. So this is unit lower triangular. And this, I believe this one down there is unit upper triangular. So a unit lower or upper triangular matrix is non-singular and its inverse is unit lower triangular or unit upper triangular, respectively. So now that we looked at the inverse of Mij already, and now we're going to get into why we wanted to look at the inverse of Mij. So, if I have the matrix MK, or actually MK inverse, so the only difference is we're going to have positive multipliers instead of negative multipliers. multipliers, and this is supposed to be a square matrix. It doesn't look like it. 1, and then like a diagonal. So this is just how we've defined it before, except this is the inverse. We've got 0, 0, and 0 is here. Okay, so this is MK inverse, and we're going to let this equal LK, so where L is a lower triangular matrix. So therefore, if we have just the matrix M, not MK, then M is equal to M n minus 1 all the way up to M1.
I'm sorry, the last row,
M n,
comma K.
yeah, comma K, sorry. Might be easier to see without a comma. M n K. Okay, so if M is equal to all of these matrices multiplied by each other, and M is lower unit triangular, then MA is equal to U. And we've seen this already, that if we multiply all of these guys by A, then we're going to get U. We're going to get U on the right hand side. But what we want to look at is how does this apply to L now? Because L is actually the matrix that we're solving the system for over here with Ly equals B. So that's what we want to get to. We want to get to a system involving A, U, and L. So let's solve this for A. So when I solve this, we're going to have to multiply on the left by M inverse. So I get A equals M inverse U. Now what is M inverse? What did we define that to be equal to? Well, if I have LK equals MK inverse, then we could say that L is equal to M inverse, right? Okay. So A, we now get that A is equal to LU. And this is the LU factorization. So since we saw, so that comes out of the fact that we saw MK inverse is equal to LK. So then we can say L is equal to M inverse. So now L is the same thing. Well, this is LK and MK. So now let's take a look at what L is altogether.
So L will just be the product, but the
Right.
other sign, right? Like the positive sign.
Right, exactly.
They
So-
were negative.
With, so we've looked at a few different things. We've looked at Mij, where we have a multiplier in the Ij element of the lower part of the matrix. We've looked at Mk, where we just stack all of those for column K. And now we take a look at just M, like I said over there, is all of these guys multiplied together. So if M is all of them multiplied together, then we can say L is L1 times all the way up to Ln minus 1. And this is equal to M1 inverse all the way up to M n minus 1 inverse. Okay? So now our L is going to look like this. Going to have ones on the diagonal. Everything up here is 0. And then this is going to be filled in with all of the multipliers. All of the positive multipliers. M32, down to MN2, up to MN, N minus 1. And here's the last one on that diagonal. M sub N, N minus 1. Okay, so there we see that L stores all the multipliers. From Gaussian elimination. So the LU factorization is essentially Gaussian elimination because we apply Gaussian elimination to eliminate or to update everything up here, and then everything that we use to update the things up here, we store down here in this bottom half, so it can all be stored together. So now we've arrived at the LU factorization. So now that we know how to get L and we know how to get U, we want to talk about how do you solve a system AX equals B when we have this information. So does anybody have any questions so far about anything?
So, we're saying, the U that you start out with, which has the M's, these M's are the negative of those, right? I mean, if they were negative to begin with, these are positive.
Right, exactly. Because they are the inverse. So when we looked at taking the inverse of those of those elementary.
Right. So is that was LK?
Yeah, that was LK when all of those elementary row matrices are applied in column K. So we call that LK, which is MK inverse.
Right, and then U is just the original U that we dealt with before. Right,
U is equal to the last updated A.
So then you do, to find the A, you do L times U.
A is L times U. So let's take a look at this. U is equal to A to the nth power, which is equal to our final M times our original A, right?
Right.
So U and N minus 1 and N minus 2 M1 times A. So these guys all make up M. Multiplying these guys like this make up M. Now we define L to be, so L is going to be the inverse of these. Now, if we look at it, let's say this, we've got U, I'm just going to erase this guy right here, and we're just going to deal with this and this. So we've got M, N minus 1, M, N minus 2, up to N1 times A. But we want a more compact way to look at this. And we've already defined L to be equal to M inverse, right? So we can look at this in another way. If we multiply, if I want a way to factorize A and I want to solve this for A, so when I solve this for A, I'm going to be moving all of these N's over to the other side, right? So actually my equal sign probably need to go here now. So to do that, I need to multiply by the inverse of each of these. So I multiply by the inverse on the left of Mn minus 1. So I've got U here still, and then I'll have Mn minus 1 inverse, Mn minus 2 inverse, all the way up to M1 inverse. And so that's how, and so this part right here, by the way we've defined L, then LU is equal to A. Does that make sense? Does that
So
answer?
before we did this, will we need to do the upper triangle first and find out the lower interval?
Yes. Yep, you do have to do that. So when you do Gaussian elimination, like the algorithm that we came up with in lab, is going to update that whole part. Now, it doesn't explicitly zero anything below the diagonal, as we discovered, but we can put in an extra step that stores the multiplier in the place. Like, so when we got rid of the 2, 1 element, we're going to do an extra step in our algorithm to store the multiplier in that place. So it actually creates the lower part and the upper part all in one matrix. And then we can use forward substitution, which is going to update B. So we do all of this for A, and then we can apply forward substitution later for various B's.
So whenever we do Gaussian elimination now, we're gonna add that extra subset LU to say B.
So
Whatever
LU,
we had and then.
whatever's below the diagonal. So, and it's an easy step too. We just put the multiplier in the place of whatever we were zeroing out. And so that also helps with storage too, because they're both stored in the same matrix. Okay. So, alright, so now we've come up with an LU factorization. So now we need to take a look at how do we actually solve a system when we have the LU factorization. So this section is called solving AX equals B. So we've already talked about how to get LU now, and A is equal to LU. Then we want to talk about how do we solve the system AX equals B. Well, if we replace A in this with LU, so then we have LUX equals B.
And UX equals Y.
Right, exactly. So UX is equal to Y. So we solve this system, which is, since we're dealing with upper triangular system, that's going to be the system that we solve to give us our solution, right? But before we do that, we don't know what Y is. All we've done is find LU. We haven't done anything with B yet, so that means we haven't done anything with Y. So we need to solve the system LY equals B, okay? So if we solve LY equals B, what type of system is this right here? Lower or upper triangular? Lower. LY equals B is a lower triangular system. So we solve this by forward substitution. So once we solve this system by forward substitution, then we plug Y in here and solve this upper triangular system by back substitution, which is what we did in lab. Once we had
First do back sub, then
No.
find Y.
we do forward substitution first.
Oh, we do forward substitution
Yes.
first,
Forward substitution first, but that does find Y.
which finds Y.
Uh-huh.
And then you plug
And
in
then we
that
plug it
Y
in.
to find the X.
Right, by back substitution.
Right.
And so the algorithm for forward substitution is really similar to back substitution. Because we're dealing with a triangular matrix, it's just lower triangular this time instead of upper triangular. So we're gonna loop over the rows and say yi equals bi, and then for our columns, we're gonna go from j equals 1 up to I minus 1, and then we have our main step, yi equals yi minus, I'm going to call this Lij, yj. And then we can end both of these loops here. But we can see that Lij is equal to Mij, since it's just the multipliers in the lower part of this matrix. So does anybody have any questions about how we actually solve the system once we have the LU factorization?
Can we just take that y and plug it into back from the backside?
Right, so you solve this system by forward substitution, and then use it as your right-hand side in back substitution. So we have two triangular systems to solve. The first one is the lower triangular system with forward substitution, and the second one is with back substitution for the upper triangular system.
That's yi equals bi, right?
Yes, yi equals bi.
For that, where that Lij equals the Mij, are we gonna get that Mij from Gaussian elimination?
Yes.
So whenever we write our code, we're gonna have that as an input.
Yeah, well actually, let's see. For this one, it's gonna be in your L part of your matrix. So instead of calling it Mij, you might want to just call it Lij, because it's gonna come from, but yeah, you're gonna input.
Oh, so we're gonna run a different code in Gaussian that gives us the L.
Well,
Or in a different one.
let's see. When in Gaussian elimination, when we store all of those, that's what you'll call them as L something. So when you store those in the lower triangular part of the matrix, you'll assign it to like Lij equals Mij, and then so you're putting them in there.
Okay.
And so this is going to need, let's see, this is forward substitution, so it's going to need your L part that you have. But you can just give it whatever Gaussian elimination gave you, because you're only looking at the lower triangular part. Another thing to note about this that's different from back substitution is that we don't have any division here, because normally when you would subtract off and then we would divide by the coefficient of whatever we're solving for. So why don't we have division here? Anybody think what's different about forward substitution that we do on this lower triangular matrix than when we did back substitution on this upper triangular matrix? So what's the difference between L and U besides one's lower and one's upper? I haven't really emphasized this too much.
Is it because it's not equal in 1, it's going to equal in multiply?
Well, what do we have on the diagonal of this lower triangular matrix? Ones. So we don't have to divide by anything because it's just divided by 1. So that's just something I wanted to point out. So L is lower unit triangular, whereas U is just upper triangular. So U actually fills in the triangular part of this matrix. Does that make sense to everybody what the structure of this matrix looks like? Okay. All right. So over here. solving multiple systems with different B's for the same A, we can be as efficient about it as possible. So, if B changes, we only need to solve two systems after we've done the LU factorization, after we have already found LU. We solve a forward substitution with Ly equals B, and then we solve a back substitution problem with Ux equals Y. So both of these are order n squared, so when we combine them, we get 2n squared floating point operations. But in comparison to 2/3 n cubed for Gaussian elimination, even if we just have to solve two systems, it's still more efficient to just get our LU and then perform forward and back substitution than it is to solve two whole systems together. So now we have time for an example, so we're going to go through an example. I guess I could have left it on that. Okay. So this is the example that we were working on in lab. So once we apply Gaussian elimination, we can see this can be reduced. So this is A. To the upper triangular matrix, U, 1, 2, 1, 1. Okay, so this is the upper triangular matrix that it's reduced to after we multiply by all these elementary row matrices. And the operations that get us there is row 2 minus 3 times row 1. And these are important, so we need to list them in the order in which we applied them. So R3 minus 4 times R1. R4 minus 2 times R1. R3 minus R2. R4 minus R2. And then lastly, R4 minus R3. So now that we can find all the elementary row matrices. Okay. And in the notes, I believe these are labeled with E's, but for consistency here, I'm going to just call them MIJ, where IJ is whatever we're trying to get rid of. So M21 is going to have the multiplier in the place right here, and it is -3. Okay. And 3-1, the next one, want to fill in on this matrix? What's my
one?
mm-hmm. Do what? Alright.
0,
0,
0,
0, 0, 1, 0. Right. And then the last one. M 4, 3. So
1, 0, 0, 0, 0, 1, 0, 0, 0, negative 1, 1.
right. Okay. So those are all of our elementary row matrices, and when we apply them to A, we get U. Yeah, we're gonna have to go to the other board to finish this example. Alright. So now that we've found all of these elementary row matrices, we have A equals LU because we've got the upper triangular part, and then we just fill in each of these multipliers. We can just combine them all into one big L now. Where L is M2 inverse, M3 M4 M3 M4 and then M4 inverse. Okay, so what goes right here? And then here.
Isn't it supposed to be positive because it's the opposite?
Yeah, you're right, it is. I'm sorry. Thank you for catching that. The inverse is positive. So 2 here, 1, 1. Yes. Okay. So this gives us L now. Where I is greater than J. Okay. So if I want to find, I also need to do the same thing to B, right, that we did to A. This part would be considered forward substitution, but we can also think about it as applying those same elementary row matrices to B as we did to A. Times B. Okay, so we're applying them exactly how we did to A. So this was the first one we applied, the second one, the third one, so on and so forth. So you'll notice that they are in different order, but that's because when we were defining L, we had to move them over to the other side to define L. So this is applied exactly the same way as we applied it to A. So now that's going to give us U, and so our original B is 5, 1, 22, 15. Okay, so now we apply all of these row operations to B. Okay. So when we apply those, we get 5, 1, 1, 3. And this is equivalent, or it is, forward substitution. So anytime you're applying something, or applying all of these elementary row matrices to B, it is equivalent to forward substitution. So even if we include it in the Gaussian elimination algorithm, we can still say that we're implicitly applying forward substitution, whereas we could also just use forward substitution algorithm too. Alright, so we're almost.
So when we're doing forward substitution for that, do we use L or do we use M?
L, yes. Yeah, so forward substitution is solving the system Ly equals B. Okay? So are there any questions so far about anything? Okay? Alright, so we're almost through this example because now we have y, so what's the only thing left that we have to do?
Solve for X.
Yep, solve for x. So, and we use what to solve for x?
Backwards substitution with U.
To solve for x. Okay. So now this is solving the system ux equals y with the y that we just found from forward substitution. So I've got x4 plus y4 divided by u4, and when we plug those variables in, we get -3 x3 is y3 minus u34 times x4 divided by u33. So that gives -2. And then x2 y2 minus u23 x3 4 x4 divided by u22, that's -6, and then finally x1 is y1 minus u1 2 x2 1 3 x3 minus u1 4 x4 divided by u11. And for this, we get 16. So now we have our solution. -3. Alright. So we want to store LU and then use forward substitution to solve Ly equals B, and then use back substitution to solve Ux equals Y. And then we have found the solution to our system. Now, like I said before, Gaussian elimination takes 2/3 n cubed, whereas forward and back substitution both take n squared. And we also discussed that LU is stored in one matrix. So our storage isn't that much either. We have this whole upper triangular part is U, also including the diagonal, and then everything down here is our L. So this is what we get out of Gaussian elimination. And then the forward and back substitution work on the upper part or the lower part, respectively, whichever one it calls for. So it's never, so we can just put this into our forward and back substitution algorithms, and it's gonna work on the correct values because of the way we set up our loops to go through. Does anybody have any questions about anything? Let's see, we've got like 9 minutes left. So I guess section for Tuesday for just, and for Wednesday for just a few minutes. So now that we've talked about how to find the LU factorization, we want to talk about when does it actually exist and is it unique? So if we're discussing when it exists, that means there are times when the LU factorization does not exist. So this is on existence and uniqueness. So not every non-singular n by n matrix has an LU decomposition. So for example, if we have a 1, 1 equal to 0, then what's going to happen? All of the multipliers for that column are undefined. So
So divide by A11.
right, exactly. So mi1 for I equals 1 to n are undefined. So no multiple of the first row can be added to the other rows to eliminate subdiagonal elements. So we can't have that happen. So if we think about the algorithm, of Gaussian elimination, the main step of Gaussian elimination, we have aik equal to aik minus mij ajk, where mij equals aij over ajj. So this is explicitly why it can't happen, because when j is equal to 1, then this right here is going to be 0, so we can't divide by it. So if we can't divide by, if this doesn't exist, we can't perform this operation for anything while we're inside this loop where j equals 1, or wherever the 0 occurs. So this causes what we call breakdown. In the Gaussian elimination algorithm. Even if A11 is not equal to 0, it can happen that another diagonal element of that row is equal to 0, which causes a similar breakdown. So then LU does not exist. So that's one major reason for what we're going to talk about on Wednesday, which is pivoting. Well, the code that you have right now for Gaussian elimination is not going to work for every single matrix that you could use. So
for
but
j equals 1 to n, ajj has to be non-zero.
right, exactly. But when we go to the lab, we're not going to go to the lab this week. We're going to be in lab next week. We're going to implement Gaussian elimination with pivoting. Then we'll have then we can talk about always having an LU decomposition for every matrix A. But what we have right now, we can't always have an LU factorization for every matrix A. So it has this diagonal element 0. So when we talk about pivoting, it can be shown that LU exists if we have what's called the leading principal submatrices, which are defined of A, defined by, so this is A 1 through K for the row, 1 through K for the column. So this is just the matrix of, it's like the upper left-hand portion of the matrix A, up till K rows, K columns. If all of these matrices are non-singular, then it says that the LU factorization exists and it is unique. Okay. So if all of those leading principal submatrices are non-singular, then the LU not only exists, but it's also unique. And so I think that's a good starting point. So we'll talk about uniqueness first thing on Wednesday, and then we'll get into the two types of pivoting, which are partial pivoting and complete pivoting. So are there any questions at all? All right. Really good to go.